All right, so section 2.4, we are talking about the precise definition of a limit. We want to actually nail down mathematically, what does it mean for f of x to be arbitrarily close to a number L when x is sufficiently close to some number a that we're approaching in the limits. Okay, so this was the problem that we were looking at yesterday, and now we actually want to flesh out what the definition of what is arbitrarily close to 5 and sufficiently close to 3 mean exactly. Now, I think I hinted at yesterday that expect this definition to look a little cryptic at first. It's going to take some getting used to, but we are not going to do this forever. We're going to learn this is what the limit is actually doing, and then we're going to learn some better tools that allow us to calculate the limits without having to do this all the time. All right. So the question we want to answer is, suppose that I say that the function that we were dealing with, that piecewise function 2 screens ago, let's say that I want that function to be at least within 1/10 of a value from positive 5. How close does x have to get to 3? This is what that definition means. Now, the distance from x to 3, the way you find the distance between two numbers is you subtract them, and you take their absolute value. The reason you take the absolute value is because the distance between 2 points is always positive. Depending on whether if x is smaller than 3, then x minus 3 is negative. But if x is bigger than 3, x minus 3 is positive. And like if x is equal to 2, the distance is 1. If x is equal to 4, the distance is 1. It just depends on what side you're on. The absolute value is just in there to make certain that regardless of what side you're on, the left or the right, the distance is positive. So the distance that the function is away from what we're saying the limit is. Again, we take the difference of those two values, and to make it positive, we take the absolute value. So what we're trying to do is, now we have just said how close we want our function to be to the number 5. We set it within, we want to be at least within 1/10 of a unit. That means that we need to find some number delta, and this is just the lowercase Greek letter delta, that so long as I am within, that my distance is, that my x, the distance that x is away from 3 is less than delta. If this is true, then this inequality will always be true. This is going to take a little work, and at first glance, it's going to appear that we're doing the same work twice. But bear with me, the first half of the problem is just to figure out what number delta is supposed to be. Once we know what delta is, now we can say, here is how we make this inequality always be true. So, this is the question we're trying to answer. If 0.1, if 1/10 is my maximum distance away from the f of x is allowed to be from 5, here's how we go about figuring out what delta should be. Well, let's suppose for now that we chose delta equal to 0.05. Where did this number come from? Don't worry about it for now. Just watch what happens if we let delta be this value. If delta is equal to 0.05, then what happened? Oh, okay. So this is the inequality. Let me back up one screen because I just can't fit it all on one page. This is the inequality right here that we're trying to show is true. So we're starting by picking delta equal to 0.05. Now let's look at what what the absolute value of f of x minus 5 is actually equal to. Remember, in the context of limits, x is not equal to 5 itself. So we're on the piece of that graph so that f of x is equal to 2x minus 1. Well, what is 2x minus 1 minus 5? It's just 2x minus 6. Factor out the 2. And now, what happens is, remember that we just said that this absolute value of x minus 3, we were setting it to be less than 0.05. If this distance right here is less than 0.05, then 2 times that value will also be less than 2 times 0.05, which is 0.1. So if we choose delta to be this value here, then the inequality that we want is guaranteed to be true. The only question now is, where on earth did that 0.05 come from? So, oops, okay. So what this line at the bottom says, this part of it says, I want you to tell me just how close our function is supposed to be to 5. If you do that, I should be able to give you a number delta that tells you that if you're at least as close to 3 as that value, then the original inequality is going to be satisfied. So you tell me how close I need to get, and I will tell you how close x needs to be to 3 in order to guarantee that that always happens. It seems like a cumbersome definition, but it is how we define the limit exactly mathematically. It's one thing to look at a limit intuitively and think of it as the function value that our values approach as x approach a, but we need to, in mathematical terms, specify what approaching a number actually means. Okay. Oh, I'm sorry. You was copying. Okay. No problem. I can back up for a little bit. Now, what I'm about to do on the next screen is, instead of this distance being 0.1, we're just going to pick it to be some very, very small number that we call epsilon. So sometimes you'll hear this kind of proof as an epsilon delta proof of a limit, because we're dealing with epsilon and delta values to prove this limit. So, like on a test, the definition might say, use the epsilon delta definition of a limit to prove, I'll give you a very simple limit to prove. I'm asking you to do exactly what we're about to do on this next step. Okay? All right. So now, epsilon, what is epsilon? It's not a variable. It is some very small number that represents the maximum distance that our function can be away from what we're calling the limit. In the last problem, it was 0.1. But it can just be any very, very small number. And essentially, that number can approach 0. It can be 1/10, 1,000, 1,000,000, 1,000,000,000,000. Just very, 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 very small. All right. So if the absolute value of f of x minus 5 is less than epsilon, here's how we're going to work this problem. If we get delta equal to epsilon over 2, which is what we did in the last problem. Remember, if epsilon was 0.1, we chose delta to be 0.05, which was half of epsilon. Then, this, if we choose delta equal to epsilon over 2, we get this inequality for free. And now, using the same kind of arithmetic from the previous screen, absolute value of f of x minus 5, I just substitute what f of x represents, simplify it, and when I get to this step, after I factor out the greatest common factor, what I am hoping is that this absolute value right here is exactly the same as the absolute value from our delta substitution. And in the problems that we're going to be working, in the basic limits that we're going to be faced with, that's going to be true in one way or another. In some cases, that's not possible, and you have to tweak your solution a little bit in order to make it work.
Is that constant?
Sorry?
Like, is that constant? Like the x minus 3? And like the
X is, this is not constant because x is getting closer and closer to 3. X is a variable.
okay.
But if we have assumed that it is less than epsilon over 2, then this expression is going to be, oops, I left off something. This is less than 2 times epsilon over 2. Because it's the absolute value of x minus 3 that's less than this epsilon over 2. But I've got this 2 here that will effectively cancel it out. And what I'll end up with is that this last line is going to be less than epsilon. And this last line is exactly what we wanted to show. If this number is less than delta, which we had chosen delta to be epsilon over 2, if that is assumed, then if we follow this line of arithmetic, that's going to show that the absolute value of f of x minus L is less than epsilon. And this last line is just a restatement of what these first two lines say. That our function, that the distance between our function and 5 is less than epsilon if our distance away from 3 is less than delta, provided that we have chosen delta appropriately. Now this value of delta is going to change depending on your problem. In this case, it just happens to be epsilon over 2. Okay. So here is the epsilon delta definition of a limit. So we're having to make some assumptions. So it says, let f be a function defined on some open interval that contains the number a, except possibly at a itself. Remember, limits don't care what happens at the number you're approaching, only what happens as you're very close to that. If that's true, then we say that the limit of f of x as x approaches a is L. That's this statement right here. If and only if, for every possible number epsilon that is chosen, greater than 0, there exists a delta greater than 0, such that if the distance between x and the number we're approaching is less than that chosen value of delta, that will guarantee that our function, the distance from our function value away from that limit, is at least as close as that epsilon value. And this last line says exactly the same thing as this, just rewritten in terms without the absolute values. So absolute value of f of x minus L less than epsilon is the same as saying this, that f of x is somewhere between L minus epsilon and L plus epsilon. Now, there's a lot of just of symbols here and absolute values and inequalities, probably the best way to imagine this is just looking at the picture and seeing what happens. Okay, so the green line is our curve. That is f of x. So let me put that up here. So this is f of x. So when I say this, right here, whoops, not that, this. What we're really saying is that as soon as that value of epsilon gets chosen, this is going to establish an upper boundary and a lower boundary. It's basically forming a target around the limit value. This is now the target that I want to hit. Right here. Anywhere in this interval right here. So the maximum value is L plus epsilon. That's this value here. L minus epsilon is right here. If we follow these lines and see where the function hits that maximum and the minimum boundary around that limit, what we can do is we can use, since this is a function, if I tell you what the y-coordinate is, we should probably be able to find the x value that caused that function value to happen. So if I know the y-coordinate, I should be able to come back and get this x value right here. Likewise, if I know this point, and I know the function, I should be able to find this value on the x-axis right here. Now notice that when I take L plus epsilon and L minus epsilon, that makes an equal size boundary on both sides. This upper band and this lower band are exactly the same width. However, look what happens when I look at the values on the x-axis. This interval is much smaller than this interval. So what's going to happen is you choose delta to be the smaller of these two distances. The reason you want the smaller one is because you want to guarantee, like for example, if I take any function value, let's say this value right here, if I just pull a number that are between these two red dotted lines, if I look at its function value, which is right about here, you can see that the function value hit the target. I'm exactly where I wanted to be. And that's going to be true whenever I stay in between those red dotted lines. But since it's a different distance on both sides, if I choose delta to be the smaller distance, what's going to happen is now I'm going to have an equal distance on both sides that if I pick a number out of this blue interval, well, the entire blue interval is guaranteed to land in that target that I wanted because it's in between the red lines. If I had chosen delta to be the larger of the two numbers, then that would have given me something that looks like this. So let me back this. Oh, I didn't realize as soon as I switch the screen, it doesn't allow me to undo any changes anymore. So this is all permanent now. Okay. If I were to choose delta to be the larger of the two numbers, watch what happens. If this is delta, then that means I should be able to go out to this value over here. This is a plus delta. But look where a minus delta would be. A minus delta would be like way over here somewhere. And now notice that there's a part of the blue interval that lands outside of the target. Everything that's right here, the function value is at this point on the graph, and that does not hit that limit target that we're trying to get to. So by choosing delta to be the smaller of the two values, that allows us to pick one number for delta that guarantees, so long as we are in that blue interval. Yes, there are more numbers that let us hit the target. But so long as we're in that blue interval, we're guaranteed to hit the red interval on the y-axis. That is what the precise definition of a limit is doing underneath all of that notation. Sorry? And while I'm here, I need to get rid of that. We're about to work a problem from start to finish that shows how to find the right value of delta. Because this function is going to be broken up into this problem is going to be broken up into two parts. The first part is to find what delta should be. Once we get delta, we should be able to prove that the right inequality, this inequality right here, holds. Just say when. Okay. All right. So, these instructions say use the precise definition of a limit to prove. Now, they're telling us what the limit is. I cannot use the limit laws. I cannot even use approximation like we did all the way back in section 2.1. How we were picking x close to 3 and then we were getting closer and closer. That was only an estimation. Now we actually want to prove that this limit is actually what we're saying it is, and that it's not some other value. So remember what the notation of the limit says. We're dealing with the limit as x approaches a of f of x equals L. So if you just pair up with what is in our limit, I can see that a is equal to -2, my function is 1/2 x plus 3, and this value of L is equal to 2. So I want to set up my problem. I want to set up those inequalities with f of x, L, and A put into their right places. So that looks like this. So this says f of x minus L is less than epsilon whenever x minus A is less than delta. That's exactly what we want. Now, when I flip this slide to the next screen, this last line that I just wrote is going to disappear. But I'm just showing that all I did was I took this line from the definition and just plugged in the values that we know. Notice that we don't know epsilon. Epsilon is going to be any positive number. Doesn't matter what it is. We have to figure out how we pick delta. This is the key part of this first problem. How do we pick delta? Based off of an arbitrary selection for epsilon. Here's how we do it. What I want to do is start with this inequality, the one involving f of x minus L less than epsilon. I want to do everything I can to get this absolute value to look like this one. Now, it may require some arithmetic. It may require some multiplication, some rules of absolute values. But I'm trying to algebraically manipulate this absolute value to look like this one. And for all of the problems that we are going to do of this type, that's always going to be possible. So the first thing I did is I just combined the plus 3 and the minus 2. That gave me 1/2 x plus 1. Absolute value of that expression is less than epsilon. Okay? Well, I'm trying to get to this. This is x plus 2. And notice I can make this x plus 2 if I multiply this side by 2. But if I'm going to balance this inequality, I have to do the same thing to both sides. So if I'm going to multiply this left-hand side by 2, I have to multiply the right-hand side by 2 as well. Now, one of our rules of absolute value says that if you're multiplying absolute value by a positive number, you can pull that positive number into the absolute value and multiply it by whatever is already here. And if I do that, this becomes x plus 2 is less than 2 epsilon. Well, now we have this, we have this expression looking exactly like this. And this is just screaming now to say choose delta to be this 2 epsilon right here. So the first half of this problem is done. We have figured out what we should make delta equal to. Well, now that we've done that, what we're going to do now is, I really should have broke this up in a couple of slides, but pretend the rest of this information is not here yet. Once you choose delta equals to what delta is equal to, go back to the delta inequality up here and substitute that in for delta. So delta becomes 2 epsilon. And now what I am trying to do is work back to this inequality right here. And you'll notice that the arithmetic is really the same thing as this done in reverse. And that is by design. Because what we are doing is we're basically reverse engineering what delta should be. I mean, we could try picking delta at random, but I ain't got that kind of time. And we could be picking values of delta for the rest of our life and never pick the right one. So if we take our clue from what we're trying to get to, if we reverse engineer what delta should be, then really at this point the work is done. Because now I've just got to say, if this inequality is less than this delta we have chosen, look what follows. Well, these two signs cancel each other. From this line, I can factor out, there's something wrong here. Oh, no, I'm sorry. To go from here to here, I just divided both sides by 2. That cancels this 2 from the right-hand side, but it puts a 1/2 here on the left. This is a positive number, so I can pull it into the absolute value. 1/2 times x is 1/2 x. 1/2 times 2 is 1. And now, I can take this 1/2 plus 1. This 1/2 plus 1 is not what I want. I want 1/2 x plus 3 minus 2. So I'm going to break this up into 1/2 x plus 3 minus 2. How did I know to break it up like this? Because this told me right here. I'm just going from this line and backtracking all the way through these steps. There's no new arithmetic to this point. So once I get to this line, what this column on the right says, if this inequality is true, which it is, then this one is true, and this one is true, and this one is true. And this last line is exactly what we wanted. So this guarantees that if I am within a certain distance of -2, this is going to guarantee that my function is within a certain distance of +2 on the y-axis. And it is this line right here that actually does the work of the problem. This line over here, this column, is just to identify what delta is. I know that it seems like we're just doing the same work twice, but this that is on the left-hand side is actually not the proof. It is the work before the work, figuring out what our delta should be. And armed with this knowledge, now we can start the actual problem, and this column actually proves it. Even though I know the two columns say the same thing in reverse, but and you can argue that this is actually not necessary, because choosing delta to be the right value, that's what's important. Whether you actually write the steps out a second time. But I remember when I took calculus like 23 years ago. And I remember doing these kind of problems. And it was drilled into us. There's the work before the work, meta work if you want to call it. And then there's the actual work of the problem. And there is a difference between these two lines, or between those two columns.
Is that what you did? Like the x minus 2,
Yeah.
That's all I'm giving the problem.
Well, this line right here, that is straight from the definition. That's not going to be given to you. So when it says use the precise definition of a limit, you will need to know that this line should say absolute value of f of x minus L is less than epsilon whenever x minus a, that absolute value, is less than delta. That is never going to change. What is going to change is what f of x, L, and a are. And those changes is going to affect what your selection of delta is going to be. In the previous problem we worked a couple of slides ago, the appropriate value to pick for delta was epsilon over 2. In this problem, it is 2 times epsilon. But for the problems that we're going to see, it is going to be some expression involving epsilon. There are slightly harder problems where you choose delta to be the minimum of 2 values, and there are some of those problems in the book, but I don't think you've been assigned any of those in the book problems that I gave you. Just like there is a two-sided limit that we saw in section 2.2, there is a precise definition for left-hand limit and right-hand limits. Now, I'm just giving you these definitions for completeness. If I ask you a problem on a worksheet or on a test, I'm going to be asking you the two-sided problem. So you might see these in homework problems from the book, but I'm not terribly interested in precise definitions of one-sided limits. Notice what changes. Everything stays the same until you get to what this inequality right here is. We're only looking at A and the left-hand side of A. Rather than going from A minus delta to A plus delta, we're only looking at the left-hand distance away from A. And that's going to be A minus delta up to A. If I go back to this picture, and I'm coming back to this slide in just a second. If I come back to this picture, that's more slides than I thought. Okay. This value right here, this value of x, this is A minus delta, this is A plus delta. For the left-hand limit, we're only looking at values of x that come out of the blue interval that you see right now, from a minus delta up to a. The right-hand limit will do just the opposite. It's going to start at a and go up to a plus delta. That is the only thing that you're going to see that changes in those definitions, apart from, well, apart from this, I'm using the left hand and the right hand limit notation. But the rest of the definition is staying the same. I still have absolute value of f of x minus L is less than epsilon. But we're only going from a minus delta to a for the left hand limit, and we're only looking at values of x between a and a plus delta for the right hand limits. So this is apparently where my last slide was. So what we are going to do is we're just going to stop here rather than me try to make up